We're continuing with section 4.7, and this is part 3. The example this time, what is the maximum area of a rectangle inscribed in a right triangle with side length 3 and 4? The sides of rectangle are parallel to the legs of the triangle. So what is the shape of this? So the sides of the triangle are 3 and 4, and the rectangle and the sides of the rectangle are parallel to the 2, the ends of right triangle. Look at this. If I move all these different rectangles that you can get, and you can see that somewhere in the middle, it seems like the area of the rectangle is the largest, and then toward the ends it gets smaller and smaller. 0 at the very end, 0 at the very end, and that's a rectangle that you can get. So let's have a fixed notation. Let's have x and y, and x to be the basically the length from this corner of the triangle to this corner of the rectangle, and then y to be the other side of the rectangle. And then notice we have the objective function. We're trying to maximize the area. So objective function is one side of the rectangle times the other side of the rectangle. We said y is one of the sides, but the other side is that 4 minus x. And so that's the objective. And then the constraint, what is limiting us in here, is that the rectangle is supposed to be inscribed in the triangle. Now, how does that affect the rectangle? And so as we saw when we were moving that point, that as we move the point right down here, the length, one length increases, the other length decreases, and so on and so forth. But there's always a correlation between them. How's that related? You have the similar triangles in here. And so what is happening is this length 3 over 4 is equal to this little length above divided by one side of the triangle, which is 4 minus x. Or the other way of saying this is that 3 over 4 is going to be also equal to this length over x. That is y over x. And so and so y is 3/4 times x. And so that's the relationship that you see. So that's a constraint. And so again, y over x was 3/4 by the similar triangles, and therefore I can replace y equal to 3/4 of x over here, and then get a new objective function. And so the objective function becomes a of x after you replace a of x equal to 3/4 of x times 4 minus x. And then domain, as you see, x cannot be bigger than 4, it cannot be smaller than 0, and therefore see, x cannot be bigger than 4 is this length, and cannot be smaller than 0, and therefore domain is 0 to 4. Best way is to take the derivative and find the critical numbers, and that would be when you take the derivative and find the critical numbers, you find x equal to 2. And so you evaluate at 0, 2, and 4, and the maximum is 3. Again, this was an example that you actually used the similarity of triangles to find the constraint. And so there usually there is for engineering purposes, there are constraints are coming from some geometric property of the problem, and so pay attention to those. And so the question though is asking, would find what is the maximum area of the rectangle, and we also want to give the dimension that gives that maximum area. And the dimension that gives that maximum area you solve for x, and that was 2. You have to again plug it back into y equal to 3/4, and you get 3/2 for y. And so the dimensions are 2 times 3